Okay, so one of the ways to include the long wavelength fluctuation that is proposed is dual fermions. So I will not go, I have a slide with some technical details, but I will skip it. And because the idea can be relatively simply explained in the following way. So assume that you write your problem in an action formalism. So the interaction U is purely local, and the hopping is between sites. So we are very much used to do Hubbard-Stratonovich transformation on the U, and then to integrate out the fermions and do things this way. So here the idea instead is to do Hubbard-Stratonovich transformation with Grassmann variables on the hopping. Then what will happen is that you will be left with a problem, an effective problem for the fermions that involves all the cumulants of the endpoint functions on a single site, and everything between sites will be in perturbation theory in 1 over hopping.
Incidentally, is also the correct starting point if you do the mean field theory of bosonic Navarre model.
Yeah, exactly.
Except in that case,
in that case, it's no Grassmann variable. Yeah.
Yeah, it's also
a lot simpler. Yeah. So I think this was invented. This method of fermionic Hubbard-Stratonovich was probably invented by my colleague Bourbonnais, and it's used now for this method of dual fermions. But what happens is that you're stuck again with the problems of doing perturbation theory. So you need to decide which diagrams you will choose and so on. So the method is not unique, and I'm not an expert on this. I just want to show you that it exists and it has to be benchmarked, and that's what work needs to be done. Okay, now I said I would talk about impurity solvers. So you need to solve the impurity problem. That's the only part that is technically difficult, or the main part. So here's an example of what we mean by an exact diagonalization solver. So you take your cluster here, and you add the BAT sites, which means sites that are not interacting, and which carry the broken symmetry. Now, if you do that, you have a finite BAT. So you cannot modify, you don't have an infinite number of degrees of freedom to modify the hybridization function, which, as I explained, is the quantity you will make self-consistent. So instead, what you do is to minimize a distance function to find the BAT parameters at iteration I plus 1. You need a cutoff also, in the sense that, again, there's not an infinite number of degrees of freedom in the BAT. So what you define the distance as the difference between the hybridization function at step n plus 1 and at step n. So I is the iteration, the cluster dynamical mean field theory iteration, or the DCA iteration. So you're trying to improve all the time your BAT. So there's a difference between the original hybridization function that you add at the beginning and the new hybridization function. You want to modify the BAT to get something better. So you take this modulus square. It's a sort of a Frobenius norm. And there's a weight here, which just means that you take a cutoff, or you weigh the low. In general, you want to weigh the low frequency, because at high frequencies, the things become trivially equal. So there are several implementation issues that are not trivial. So the exact analyzation code uses Lang-Schoes or Ban-Lang-Schoes or Arnoldi methods to find the ground states or a few excited states. Integrations are difficult. You need to do them and the imaginary plane. It's better to do them in the imaginary place in the case of frequencies. And to show your result, you need to have some Lorentzian broadening for the dynamics. So we know by experience what is the good Lorentzian broadening, in the sense that you can, you can look at different shapes of clusters and things like that, and see where the results become independent of the Lorentzian broadening. You may have difficulty to make the bat converge, but that's not specific to exact analyzation. It's sort of something very general. So what you do is you start from known or easy solution. So you start from a Hamiltonian where you can find the bat parameters and converge things, and you do small changes on your Hamiltonian to until you iterate to the final solution. So for example, if you want to treat a case where the hopping would be anisotropic, you start from the case where the hopping is isotropic and you find the solution. Then you modify a little bit the hopping parameters and you look for a different solution. So here are some references. It started with Caffarel and Kraut in 1994, and there's been all sorts of progress. I recommend the lecture notes by my colleague Sénéchal. Okay, benchmarks. These red points are the value of filling as a function of chemical potential for the one-dimensional Hubbard model at strong coupling. So this is the bandwidth for the one-dimensional Hubbard model. There are only 2 sites in the cluster and 8 bat sites. And the solid line is the Bethe-Ansatz solution. So you see that it's pretty well. And these are other methods like single-site dynamical mean field theory, and we don't need to worry about all these other methods. And you can also have a quantum Monte Carlo solver and see that indeed this is the solution for 2 sites. So it could be here that we parameterized the bat and made the thing work, but the point is that you do the correct solution for 2 sites with the quantum Monte Carlo solver. You do get the same as what you got with exact diagonalization. Yeah. Yeah, I wouldn't claim that. I mean, the quantum Monte Carlo solver here is the Hirsch-phi, so there's a delta tau. You need to extrapolate to 0. So it has its own things. I wouldn't take these differences seriously. Okay, now continuous time quantum Monte Carlo impurity solvers. So let me remind you of a few things about the quantum Monte Carlo. So we want to evaluate a partition function with that would be e to the minus beta h here, and you want to average some quantity with this weight. And in Monte Carlo, what you want to do is to generate configurations. X is some living in some space of configuration with the same probability as the one that appears here. And then the Monte Carlo average is just some overall configurations that were generated. If you're not able to work with this probability, the real probability, what you can do, and you can work with a probability rho, let's say, is that then in that case you get a similar formula, but you need to, to do this thing here, to multiply and divide by the same thing, and you will obviously need to modify the denominator in the same way. So you get it this way. So now the Monte Carlo is done with a Markov chain. So there's an ergodicity issue, and the main thing is detailed balance. So what do we mean with detailed balance? We mean that the probability of going from a configuration X to a configuration Y divided by the probability of going from Y to X is just the ratio of these equilibrium probabilities for configuration x and y. In other words, just cross-multiply this. So px times wxy equals py times wyx. So if you're in equilibrium, it means that you have as many transitions one way as the other. Now, the transition probability is given by a proposal probability, so the proposal to change from x to y, and an acceptance probability. So you're left, in your Monte Carlo procedure, you're left with a lot of freedom here in defining how it will work. So the Metropolis algorithm is that the acceptance probability is given by the minimum of 1 or the ratio x over y, which is basically this ratio, but taking into account this proposal probability. Now, why do I go through all of this? The reason is to show you how you can do continuous time quantum Monte Carlo. So how can you do Monte Carlo in continuous time? Remind you of simple facts about perturbation theory. So you can always write this operator like this, where the evolution operator obeys this differential equation that you solve iteratively this way. So if you apply this to the partition function, you will know, suppose you could expand in interaction, you could expand in hybridization, and these are the main two categories, but here I will focus on expansion in hybridization. So if you do this, then you see that you have to evaluate a sum over all powers of the hybridization evaluated in the cluster Hamiltonian. So in other words, your configuration, the configuration space I want to move into involves imaginary time and involves positions or momenta or whatever is there. So my configuration space involves these imaginary times. And I have to move from, let's say, order k in perturbation theory into order k plus 1. So my x here of configurations, as I said, involves spins. It can involve momenta. It can involve, here k is not momentum. K is the order in perturbation theory. Gamma is all the other quantum numbers. And tau is the different times here corresponding to order tau. So the weights, the p, the probability that I'm interested in is these weights times the d tau. And now I'm showing you this because there's a sort of a miracle that occurs, which is that if you look at, let's say this is imaginary time, and I have two operators here, one at tau 1, one at tau 2, and I want to add or remove operators. So the proposal probability here for going from perturbation theory order k to k plus 1, in other words, if I want to insert another parameter, is proportional to d tau over beta, because it will depend where I put it. The removal probability is 1 over k plus 1. If this is order k, this is order k plus 1. So I have k plus 1 points that I can remove. So this is this. So if you work out now the algebra with these proposal probabilities and the p that involve the d tau, then you can see that the d tau that comes in these probabilities just drops out with the d tau that is there. And the acceptance probability, this R that's computed in the Metropolis algorithm, depends only on weights that don't involve d tau. So these are some references, and let's now look at solving the cluster in a bat problem for this hybridization expansion. So there are three algorithmic improvements that we did on this standard algorithm. So here I just repeat that you expand in powers of the hybridization. The reason I do this repetition here is to remind you that the H0 here now will involve the bat and the cluster without any hybridization between them. The hybridization is here. So if you do this, then it means you can evaluate this average over the hybridization will factor into a piece that involves only the cluster. This is these D's, the hybridization between the cluster D and the bat A, and something that involves only the A's. You see this V hat here is the hybridization times the bat. So this is non-interacting, so it's easy to evaluate with determinants. And the tough part is to evaluate this trace here over things on the cluster where there's no Wick's theorem. Okay, so one thing is that you can reduce the sign problem by choosing the basis appropriately. For example, on this triangular lattice, well, you can simplify the trace a lot by using eigenstates of the Hamiltonian on this cluster. So this will make the Hamiltonian block diagonal. In cases here, like here, where the one irreducible representation comes in twice, you can choose the angle to minimize to optimize the sign, and you see that it has quite a huge effect here. If you can go from okay, why am I talking about average sign? Because sometimes the sign is of the determinants or the traces is +1 or -1. Then you cannot use, it's not a positive quantity, so you cannot use it to do the Monte Carlo algorithm. But if you take the absolute value and take the sign into the observable, then you can use the trick I just showed and things will work out. So the average sign is 10 to the -4 here up to something that's close to unity. So choosing an angle can have a very big effect. The angle, because the irreducible representation A1 comes in twice. So you can choose, you have a 2x2 matrix that is in general anything. So you can do a rotation of the basis within these two A1G representation. Pardon me? Yes, you're right. That's something else you need to check. But yes, you're right. But in practice, we haven't done, I cannot show you a detailed study to show that it works. But I can tell you that we are completely unable to do the simulation here, and here we can. So, yes. Now, another trick is that again, I repeat these same things. We expand. Here is nothing new. Another thing is that suppose I look at fourth order in the hybridization. And suppose I have D-wave superconductivity. On the cluster, I never break the symmetry. Nevertheless, this expectation value is clearly different from 0. Because if I take D up for 0, well, if you look at all the quantum numbers here, in the downspin, I destroy in 0 pi, but this is equivalent to pi 0 because it just differs by pi pi, and here too. So it's an expectation value that won't vanish. And you find it in general, so you need to take it into account, because this hybridization function, this anomalous hybridization function for superconductivity is non-zero. But the point I want to make is that if you want to reach this configuration just from a case where you have, let's say, 2 downspins only, you see it won't work, because you have these this expectation value is 0. What I said earlier, I'm sorry, I got confused, but definitely this 4-point function is non-zero, but if I take just 2, it is 0. So I cannot reach it by adding and removing a d dagger. So you need to do 4-point updates. Finally, I'm going to finish with this. One algorithm. This is true in any states that break it's true in the superconducting state, D wave, but any state that breaks the spatial symmetries. Sometimes there are cases where you will have to do 8 updates to be ergodic. So it's quite and Olivier has examples with spins also. So this point here is quite general for any Monte Carlo algorithm. Suppose you are in a case, let's say you have long-range forces or God knows what, where your rejection rate is very large. Okay, so you try configurations, but you reject many configurations. And suppose it takes a long time to compute the rejection, the ratio of probabilities. Like again, if you have long-range correlations, or if you need to compute these traces. Then in that case, the best way to proceed is to, instead of computing the ratios of determinants or whatever you have, and then throwing a random number and deciding if you accept or reject the move, you first flip the coin. So you first draw a random number between 0 and 1. And instead of computing the full ratio that you need for Metropolis, you compute just bounds. And you refine your bound, and then you see that you can never exceed your random number. You know that this will be rejected. In other words, if I improve the bounds, this will decrease, but it will never go above this, and you know that you need to reject so that speeds up the calculations a lot. Finally, okay, this is more technical. I will not go into many details, but just tell you that when we compute these weights, I told you that the bat is just determinants, but everything that comes in the cluster, there's no Wick's theorem. So you need to compute this exactly. So the way it's done in practice is to diagonalize the Hamiltonian on the cluster and compute the matrix elements of destruction and annihilation operators in that basis. So that gives you a matrix. And the time dependence, because you are in diagonal basis, is trivial. It's just exponential of minus the energy of the eigenstate times tau. So this is the P here is the propagation, and F is the matrix representation of a creation operator. And same thing for destruction operator. So the way you can accelerate the evaluation of this trace is by remembering product of matrices you have done, before you insert or remove operators. And because it is entering a lot into details, I will skip this. It's called a skip list. But the idea is that if you use any three structures, not only this, skip list is easy, but it's probabilistic data structure that is taken from computer science. But any three structure where three in the sense of TREE, not the number three. Three, if I spoke English correctly, there would be a difference, but here I'm sure you can't make the difference quite. So you see, you keep in memory some of the products you've done at the lower stage. So these are, let's say, you have all these representations for the creation and annihilation operator, these matrix representation. So you can do the matrix multiplications by group here. And if you maintain, so this is about adding and removing operators. So, but if you keep the tree structure, it makes things much faster. And here I want to show you how fast. It turns out that this fast rejection algorithm, this lazy, we call it, combined with skip list, we call lazy skip list. The speed up that you can get is quite spectacular. You can in fact, it has beaten Moore's law. I mean, if you look at when the algorithm was invented and when you get this, you get better improvement than what just Moore's law will give you. Now, this algorithm is important because it's the main one that is used in real materials calculation. So, for example, this is a calculation for lanthanum nickel oxide, and this is a calculation for iron telluride. And this is what you can do, the speed up you can get just with skip list or just with the lazy trace. And what you want here is the lazy skip list, and there are so-called efficient and inefficient updates. But the point is that if we look at this, which is sort of doing the best you can, you see you can speed up the calculation by a factor 640 here, or here a factor of 27 in the case of iron telluride. Why is there such a big difference between the two? It's just because in the case of LNO, if you look, you plot here all the eigenstates. So it looks like an histogram because there are many eigenstates. And you see that the weights, the sector weights, you can have the density matrix and give you the probability of each of these states, is such that there are lots of states that don't have any high probability. So they are rejected a lot when you try them. So if you just do a standard adding and removing operators, then you go to this blue, you try a lot these states that are not important. If you go with this lazy trace evaluation, then you reject these states immediately, and you need to compute only the ones that are in blue. And when you take the lazy skip list, then you get the red. So you get much fewer evaluations. For iron telluride, it's the histogram is much broader, so the speed up is not as fast. So there's maximum entropy analytic continuation. I clearly don't have time to say anything, but just look on ConMat. In a few weeks or months, there would be. We will make a software that should be user-friendly. A lot of time is spent, 2/3 of the time is spent in making it user-friendly for analytic continuation of numerical data, and the program will be publicly available. Do you want me to take 10 minutes for this self-energy functional, or should we stop? You feel free to leave if you're sort of tired of hearing me, but otherwise I can take 10 minutes to explain this self-energy functional and how it leads to the equations for cellular dynamical mean field theory in a simple way. So if you want, you can define a free energy That's a functional of a source field that is minus t log of z. So what is z? Z is the trace of e to the minus beta h minus mu n. And the way this source field comes in is that you take just a time-ordered product of exponential. That's the one I introduced last time. 1 bar, phi sigma of 1 bar, 2 bar, psi of 2 bar sigma. So when phi equal to 0, this is the self-energy, the free energy. So the usefulness of this is just that I can use it as a generating function. So if I take the functional derivative of this with respect to the phi sigma of 1, 2, 1 over temperature, I get the Green's function for this problem. And the Green's function is, again, a functional of phi. Now, in many-body theory, it's easier to, or it's perhaps more natural to work in terms of the Green's function instead of these source fields. And in this case, what you use is the Legendre transform of this free energy. So instead of using phi, you use the conjugate variable g. So the way to do this Legendre transform, is to define a functional of g like f of phi minus trace of phi times g. And here, the phi is you eliminate by using this equation. So you can express everything in terms of g, like you do in thermodynamics. And what is meant by trace here, trace of phi g is just equal to the temperature times phi 1 bar, 2 bar. You remember that the bar meant summing and integrating over everything in sight. So if you do this, it's the usual property of the Legendre transform is that delta omega delta g 1, 2 will be equal to minus phi 2, 1. But we know that from the equations of motion that g minus 1 is equal to g0 minus 1 minus phi minus sigma. So this is general. Whatever the phi, this is what we have. So if I look at, I can rewrite the phi here as g minus 1 minus g0 minus 1 plus sigma. Now the real free energy that I want can be evaluated from this if I just set phi equal to 0, right? Phi equal to 0 is the free energy I want. So that's the extremum principle I was talking about. So if you functionally differentiate this omega with respect to g and put it equal to 0, then you have the solution of your problem, and basically you're satisfying Dyson's equation at phi equal to 0. So what is this omega? This omega we can write as omega of g. Now, you need to be more rigorous, but I try to convince you that you can guess the answer. So the answer is that this would be trace of log of minus g minus 1 over g infinity to the minus 1 minus trace of g0 minus 1 minus g minus 1 times g plus phi of g, where now I'm going to explain what I mean. So you see, if you take the functional derivative of this omega with respect to g, then you will get here g minus 1. You need to be careful about what you mean by functional derivatives and so on. But you just need to go to the eigenbasis, basically, and the derivative of the log is 1 over g. And this is just for convergence purposes, and if you want to evaluate this directly. But this is a detail. We can forget this. Usually people don't write this, but this doesn't mean anything. It doesn't converge. Now, if you take the functional derivative of this with respect to g, that's 1, so that contributes nothing. But the functional derivative with respect to g gives you the g0 minus 1. And the phi here of g, so phi of g is just defined in this way. Phi of g is such that the functional derivative of phi with respect to g 1, 2 is equal to sigma 2, 1. So this is what you call the Luttinger-Ward functional. Now, what it means in practice, I mean, how would you, if you wanted to compute this, what would you do? One thing you could do is, in the interaction term, you could replace u, if you want, by lambda u, knowing that the solution you want is that lambda equals 1. Then you can use a property of Legendre transforms, which is that the functional derivative of f with respect to lambda at fixed phi is equal to the functional derivative of omega with respect to to lambda, again, not the functional, just the derivative, I'm sorry. Derivative of lambda of this with respect to lambda at fixed g. Now you see that at fixed g, when I differentiate with respect to lambda, this won't change. The only thing that will change is this phi. So now what I have is a differential equation for phi as a function of lambda at fixed g. And this df d lambda, I know precisely what it is. It is just the expectation value of the interaction part of the Hamiltonian, 1 over lambda. So you can find this phi by integrating the potential energy for different lambdas. So it will look like just looking at connected diagrams. Now I just have 4 lines of so is this okay? I just have 4 lines of algebra now for cellular dynamical mean field theory. So I mean, this is done in much more detail in the review written by, in many, many places, but there's a review written by Gabi and Olivier, and this is done solidly. Now, the self-energy functional is just that you write this in terms of sigma instead of g. So now it's not a Legendre transform. You're just changing variable, assuming you can do this. So then you would get a functional of. So this is like assuming that you can invert this equation. So there's a functional of sigma, which is just trace of log of minus g0 minus 1 minus sigma over this convergence here, minus a trace of sigma times g. But what I mean by g here is, again, in terms of sigma. So all of this depends on sigma, and then plus some functional that is not the same as this, but I commit the usual sin of physicists by using the same symbol for the function. Now what we want to do is, this is the functional that is universal. If you look at this here, this combination, this is what I call F. Unfortunately, this is not the free energy like here. Let me use another symbol. In the notes, I wrote that this was F of sigma. And this functional is universal in the sense that it's a functional of sigma and does not depend on the one-body part of the Hamiltonian. For the same reason that this Lottinger-Ward functional, using this argument, in terms of coupling constant integration, gives me a set of diagrams, that looks like the diagrams with the potential for the potential energy. So these diagrams depend functionally on G, clearly, but the one-body part of the Hamiltonian enters nowhere, and that's what we have here. Yes?
So, okay, now this one, of course, from 5G, the full propagator, but 5 sigma.
So, no, because what we assume is that, and that is probably not correct in general. I mean, like here, I did Legendre transform, and Legendre transforms assume that the function is convex, and the functions here, functionals are in general not convex, and some problems I think that you encountered are probably related to this, that you cannot go back and forth without any problem. There are some bifurcations, but the point is that if you could solve this equation, sigma would just G would be some functional of sigma, and that's all that we do here. You replace the G here by some functional of sigma, which I don't know how to draw anymore. Yes, absolutely. Yes, that's I said I committed a sin here, but that's what I mean, yes. Phi of G of sigma. Cannot be. There are points where there are two solutions. Yes, exactly.
Maybe I can make a brief comment on that, which is that I don't think the function of sigma has as many problems as the function of G. Is that established? I wouldn't say established, but that's an argument. But anyway, for all these former things, this double validness is not a real problem. You can always specify it this way. I mean, it's a problem in computation if you really want. No, I just want to
the problem occurs when you try to go from G to sigma. This is where it's called. When you think, okay, knowing G, I can kind of keep it defined sigma. This is not open. So when you write this, the right-hand side line, this is where it changes in practical calculus. Now, for practical reasons, but for formal reasons, you can say, well, I will confine myself to the correct solution.
So now let me divide the system. So this does not depend on the one-body part of the Hamiltonian. So let me now be drastic and change the one-body part of the Hamiltonian in such a way that I have these disconnected clusters, to which I can add a bat or anything. But so then I will have an omega prime of sigma for the problem I know how to solve, which is these disconnected cluster, which will have trace of log of minus G0 prime. Okay, so here is G0, now it's G0 prime for this modified cluster divided by, okay, this again is just some number that is there for convergence. And now I have plus this f of sigma. So now what you can do is just replace, see, this is f of sigma. This is the same f of sigma because it does not depend on the one-body part of the Hamiltonian. So what I can do is I can replace the f of sigma that is here just by the difference between these two Okay, so this is not very complicated algebra. So this is equal to F. So so here I write that this is plus omega prime of sigma minus trace log of minus G0 prime minus sigma divided by this number. And now I'm ready to do the extremization. And the way you do the extremization is just by taking the derivative of this with respect to parameters that are in the one-body part of the Hamiltonian, let's say T prime. Now, suppose I'm differentiating. So suppose that, just to give a simple example, suppose that this is the chemical potential here. If this was the chemical potential, you know that the derivative of this with respect to chemical potential is just the number of particles. And if we differentiate this with respect to the chemical potential, you will get the Green's function, and you will be computing also the number of particles from trace of G. So this, for any piece of the one-body Hamiltonian that enters in the G0 prime here, this cancellation between this and this will occur. So the only thing you're left with is to differentiate, is to use the T prime dependence of sigma of this and of this. So when you do this, you see that you will get a trace of, okay, so 1 G0 minus 1 plus sigma times d sigma dt prime. And then you will get the same thing here, except that now you will get a minus sign of 1 over G0 minus 1 prime plus sigma. This is not a prime. This is like a dot product, if you want, times d. It's just using the chain rule, dt prime. And here the trace you have to do. This involves this integral over k tilde, and here the trace also you need to do, but there's simply the number of cluster that comes in. I mean, here there's a trace cluster, and here's a trace lattice. But I mean, the trace cluster just gave you this NC. So now the point is that you can factor this d sigma dt prime. And one way to set this equal to 0 is to consider this as a dot product and to say that the magnitude of the vector is equal to 0. And that's the DMFT, CDMFT condition for self-consistency. Okay, so to conclude, I thank my collaborators, the people with the computers, the funding agencies. Mais en premier, j'aimerais vraiment remercier le Collège de France et puis Antoine de m'avoir donné cette opportunité. En fait, je crois que c'est une opportunité unique dans la vie d'un scientifique d'avoir ses collègues de haut niveau, comme vous l'êtes. de m'écouter parler pendant 6 heures, ça ne se produit jamais parce que finalement, on va à des workshops ou des conférences où quand les gens nous ont entendus 20 minutes, ils ne veulent plus nous voir. Donc ici, vous m'avez donné l'opportunité de parler de ces travaux qui me sont chers, évidemment, qui représentent celui de beaucoup de personnes qui ont collaboré avec moi. Donc, qui représentent les travaux presque des 20 dernières années. Et puis, j'ai vraiment apprécié votre présence et j'espère que si vous avez des questions ou si vous voulez corriger des choses que j'ai dites, que vous n'hésiterez pas à me le dire et puis même qu'on pourra établir des collaborations avec plusieurs d'entre vous. Alors, merci beaucoup.